Hey everybody, how's it going today? Which face do you want to be taught statistics with today? How about this one? This is very statistician. I feel like this is kind of what your everyday statistician looks like. So maybe we'll go with this for the introduction. Today we're going to be talking about the sampling distribution of the sample mean. So just like last time, I'm going to make some notes associated with that, and then I'll show you some Excel to show you how we actually implement this stuff, because it's kind of good to see just simple versions of this in notes, but the way this is always implemented in the real world is going to be in Excel or with some other more advanced computer software. But just as a reminder, last time in the first video, we showed that sample means once you get a big enough sample size, and as the book explains, a sample size, you probably want at least 30 observations. So if you're interested in guessing the population average height of human beings, you probably want to try to get at least 30 people and measure them. Because what happens, and the book has a really nice graphic of this, is once you get up to 30 observations, pretty much no matter what that underlying distribution looks like, whether it's like our die, or our dice, which were have that uniform distribution, or the incomes of people, or the people going to Walmart, no matter what the underlying distribution of individual observations look like, once you get up to 30 observations, you're going to get this nice bell curve. And we really want to get those nice bell curves because that's where we can start getting the power of statistics. So the first thing we're going to go over today when we talk about the sample mean and its sampling distribution is, so let me just talk a second about what sampling distribution means. So as you learned in your last class, random variables come from distributions. Like those die came from a uniform distribution, but then once we took averages, they came from a bell curve shaped distribution, and that's usually called a normal distribution, but sometimes it'll be what's called a T distribution, which we'll talk about more later. So the first thing we want to know about the distribution is there's two things we care about in distributions. First of all, where is the center of it? The center of it is kind of going to be what we call the expected value, and how spread out is it. So we want to get a measure of how spread out this distribution is, which is kind of represented by that arrow, and we want to get a measure of where its center is. So it turns out that to get the best guess of where that center is, we produce a point estimate. So say you're trying to guess what the population average height of all humans is. So one way to do that would be to measure every human on the planet. And then you would get your hands on the population estimate, the population mean, because you literally would have measured everybody in the population, and you'd add up all those heights, and you'd divide by the number in the population. Now, there's a lot of good reasons not to do that. One is that it's going to be incredibly costly and time-consuming to measure every human on the planet. It'll probably take more than a lifetime, right? Another reason is if you tried to do that, you'd probably introduce a lot of error in your estimates. Like you would end up doing a pretty bad job measuring people if you were trying to measure everybody. So a different way might be to take a sample, a smaller sample of people, and then produce what's called a point estimate to try to estimate the population mean instead of trying to measure every single human on the planet to actually get your hands on the population mean. So when you take a sample and you use that to estimate the population mean, we call that thing you're estimating, that number, the sample mean, because you're not measuring everybody. You're just taking a sample of people. And the book goes over some good ways to take samples of people. I'm going to skip over that part, but you will have a couple kind of straightforward homework questions about actually taking what are called random samples. But first, let's suppose we took a sample of 3 people. You would always want to take a bigger sample than this. Like I said, you'd want to take 30. But just to show how to calculate the sample mean, say I take a sample of 3 people, and so x1 is going to be the first height in my sample of 3 people. And let's say I get 60 inches for x1. For x2, I get 55 inches. And for x3, I get 65 inches. So I got 3 people in my sample, and now I'm going to take my sample and use it to estimate the population mean by calculating the sample mean. The sample mean is usually designated by x bar, which is why I put an x bar down here. That equals 60 plus 55 plus 65 divided by 3, because that's n. That's our sample size. And we add up all of the observations on our sample and divide by n. That's how you get a sample mean. And in this case, x bar equals 60. Now, what we want to notice is that that x bar is not necessarily exactly the same number as the population mean, right? Because if I took a different sample of 3 people, I probably would not get the same number. I would probably get a different x bar. So x bar is a random variable. That's a really important fact. X bar, the sample mean, is a random variable because it varies randomly from sample to sample. Now, random variables come from distributions. And as we talked about last time, the distribution of sample means looks like one of these bell curves. So it's not exactly clear where this 60 landed in this bell curve, but that is our point estimate of the population mean. It might not be a very good one because we took such a small sample, but that's what we refer to as the point estimate. And what are we estimating? The population mean. It's called a point estimate because it's one number. We will differentiate between what are called point estimates, like this one number, and interval estimates, which we'll get to in chapter 8, the second chapter. But this is just simply how you calculate the point estimate. Later in this video, we'll calculate the point estimate for a much bigger sample in Excel. So the first question, or the first thing we care about, is the center. So the expected value of the sample mean. So we have this random distribution right here of sample means. The expected value is the average of the averages. So the expected value is like, what is the average of the x bars? Because that's one of the things we care about when we're talking about a random variable, is what is the average of that random variable. Another really expected value you can think of as another way of saying average. So if I did this over and over again, took 3 samples like this, or samples of size 3, over and over and over again, billions of times, and then I took the average of all the different x bars I got, eventually I would find that the expected value of x bar of the sample means equals mu. Mu is a Greek letter that we use to designate the population mean. So the center of the distribution of our sample means is mu. And that's a good characteristic because that's what we're trying to estimate, is the population mean. And it's good that the center, or the expected value of our sample means, is what we're trying to estimate. And that's how we could draw that graphically. So mathematically, we say the expected value of the x bars equals mu. One way to draw that graphically would just be to say, hey, the center of this distribution is where we want it to be. It's the population mean that we're trying to estimate. Now, the second question that we usually ask about distributions of random variables. So first we ask, what's the expected value of this random variable? Or the average of the random variable. The second thing we care about is how spread out is this random variable. And as you know from your last class, the way to measure that is to get the standard deviation. So when we're dealing with point estimates, whether they be sample means, we're going to look at sample proportions in the next video, we generally refer to the standard deviation of any type of point estimate as its standard error. Okay? So in the case of sample means, the book calls the standard deviation sigma x bar. So that equals the standard deviation of sample means, which generally is referred to as the standard error. So in the future, I will call this the standard error. And so you just kind of have to remember, when we say standard error of x bar, what we really mean is the standard deviation of the sample means. We kind of want to differentiate that because sigma is the standard deviation of the underlying sample. Or of x. So instead of x bar, that's the standard deviation of x. And actually, this is what's called the population standard deviation. And I think I mentioned last time, we usually don't know what that actually is because it's kind of weird to assume we know the population standard deviation when what we're trying to guess is the population mean. So oftentimes we're going to use what's called S, which equals the sample standard deviation. And we'll go over this a lot in the future, but just to distinguish between sigma is the population standard deviation of a random variable, S is the sample standard deviation. It's kind of like the difference between mu and x bar, but instead of for the center, for the spread of the distribution. Now, once we know the underlying standard deviation of individual values, that's kind of how you should think of sigma or S. We can calculate the standard deviation of the sample means, which will be smaller, using one of two different formulas. So the simple one that's the most common is that sigma x bar equals sigma, the individual standard error, so the standard error of, this individual standard deviation, the standard deviation of individual values, divided by the square root of n. Now, sometimes if you're dealing with what's called a finite population, so finite population means there's only so many of that thing. So maybe we're looking at Walmarts in Utah, average number of people that go to Walmarts in Utah. Well, there's a finite number of Walmarts in Utah. There is not an infinite number. And in that case, you have to use a special formula. So this is for infinite populations. And they actually don't have to be infinite. They just have to be big enough so that you can apply this formula. And generally, they are big enough. But there will be some homework problems that have finite populations. So that would be if you're dealing with a relatively small population and taking an even smaller sample from that population. And you have to make an adjustment for this standard error, which is the square root of n minus n over n minus 1. And then that gets multiplied by that same number, sigma over the square root of n. So this will come up in the homework. We'll never use that in our other applications, but it does show up in the homework one time. So I'm going to focus on this one mostly. So one thing I like to point out is what's with this square root of n? So as we can see, when n increases, and we saw this in diagrams before, as n increases, so maybe we have this as big spread out distribution of x bar, and that one's going to be small n. So that's for a small sample size. Well, what do you think is going to happen to this distribution as we get a bigger sample size? Just like when we were looking at the dice in the last video, the probability of extreme values is going to get smaller. The probability of values close to mu, the truth, is going to get larger. And so this is going to be our large n. Large sample size distribution. So as n increases, the spread of the distribution gets smaller, right? Because we're going to have lower probabilities of extreme values out here and higher probabilities associated with the center of the distribution, which now we know that's mu. In either case, the center of the distribution is mu. But we're going to get better guesses because we have higher probabilities of being close to mu when we have larger sample sizes. This is the benefit of larger sample sizes. Now, one thing I like to point out, and this is kind of related to economics actually, is the diminishing marginal value of information. So n, sample size, let's put that on that axis, and the square root of n. So let's explain why instead of just dividing by n up here, we're dividing by the square root of n. Suppose you have a sample size of 2, and you have the opportunity to add one more person to your sample to guess the average height. That's going to be a lot. That's going to add a lot of valuable information. You're increasing your sample by 50%. Now let's imagine you have 1 million people already in your sample, and you have the opportunity to add one more person. Is that going to be as valuable as adding one person to a group of 2 to a sample versus one person to a group of 1 million? No, you're going to get a lot less extra value or marginal value when you add one person to a sample of 1 million than when you add one person to a sample of just 2. So that means when you have really small sample sizes, you get a lot of value. So that slope is steep. You're getting a lot of value out of adding people to your sample. But if you remember from algebra back in the day, what a square root function looks like, once you have a big sample size over here, adding additional people doesn't help nearly as much. That's why that slope is decreasing. That's why we're taking the square root of n. So although the math might seem complicated when we look at these formulas, if we step back to think about it, it makes total sense. Adding people when you have a small sample size is very valuable. Adding to a sample when you already have a large sample size is less valuable. So the degree from which we go to red to blue gets smaller and smaller by adding to the sample when we already have a large sample size. All right, so just to review real quick, we use the sample mean as a point estimate to the population mean. And that's just a matter of adding the stuff up and dividing by the number of stuff. So adding up each observation and dividing by n, which we did right here for this really small sample of 3. The expected value, or the average of the averages for sample means, is the population mean, which is a good thing because that's what we want to guess, is the population mean. And our distributions of sample means here are centered at the population. The other thing we care about when we're dealing with random variables like sample means is how spread out the distributions are. And then we've provided the formula for what's called the standard error, which again is the standard deviation of sample means, called the standard error of x bar, or the sample means. That depends on how spread out the underlying distribution is, sigma or s, if we don't know the population standard deviation. We have to make this adjustment if we have finite populations. But then as we see, the degree to which this gets less spread out. So it gets less spread out when we have bigger sample sizes, which is a good thing. But the degree to which large samples help us decreases the larger our sample size gets. All right. So thanks for listening. I'm going to add some Excel to the backside of this video in just a second. I think I'll be able to splice them together, but I might have to send you 2 different ones. We'll find out soon. Hey everybody, so this is the second part to lecture video 1.3. The first thing that I'm going to do is show you an important resource that's available to you, especially because I'm going to use it in the Excel in this part of the video. If you go to the files in Canvas, there is a sheet called Excel Tips and Tricks. One of the very first thing that I show you how to do on that sheet is adding the data analysis Toolpak to Excel, which you can do with whether you have a Mac, which I'm using, or Windows. And this explains how to get that. I'm going to use that today. And you will definitely need to use it later in the semester. You can also use it now. There's a lot of stuff that it can help you on with the homework. But that's something I'm going to use today. The very first thing in Excel Tips and Tricks, this file in Canvas, shows you how to get that. So now, here is some data that we're going to use to look at some sampling distributions of sample means. So we're going to use Excel now to estimate a sample mean, which is going to be our estimate of the population mean, right? Also, we will look at a histogram of the underlying data just because I want to show you how to do that. So I've already gotten that a data analysis Toolpak. Once you have that, if you click on your data tab up here in Excel, you'll get this button over here that says data analysis. We're going to use that to make a histogram today. So today we're going to estimate, this is brand new data that I just got off the internet about coronavirus cases. I want to look at total cases per 1 million population. So let's estimate the total cases per 1 million population in different countries around the world. So the first column of this spreadsheet shows us countries. Let's make that bold, and then we can see that those are the titles of the columns. There's a bunch of different data available here. It makes sense to look per 100,000 in this, per million population in this data, because bigger countries are going to have more cases just by definition. And so I also noticed that that's a complete data set while there's missing data for some of these other values. But later on, this would be a cool thing to do a project on in class because there's a lot of data available related to coronavirus. We'll talk about the project more in the future, but data for it is widely available, so it might be a cool thing to use for a project. So the first thing I'm going to do, because I'm going to make a histogram, is I'm going to calculate the max from this column. So I can do that with a formula called max in Excel. So max equals max. That's how we do a formula in Excel. We write equals and then the name of the formula. And I have some other formulas that are valuable in that Excel tips and tricks sheet as well. And then I just go ahead and I click on the column of the data, or if it was in a row or whatever. And now this will give me the maximum number of cases in that column. Let's also do the minimum number. That, of course, is going to be equals min for minimum. Click on the same thing. And now I have the minimum and the maximum. So that's a pretty big spread. We have some countries with less than one case per million people. And we have some countries with over 17,000 cases per million people. Then let's go ahead. The reason we have to do this is we have to make something called bins if we want to make a histogram, because a histogram counts the number of observations within different ranges. So we have to tell Excel what we want those ranges to be. It looks like it makes sense to start at 0 here. So let's do 0, and then maybe we should go up by 500. And what's cool about, one cool thing about Excel is once I do 0 and 500, Excel will recognize that I'm counting up by 500. So 0, 500, 1000. And then I need to keep going until I get above this maximum. Otherwise, that maximum will have nowhere to go. So we're at 11,000 now, 14,000. Here we have 18,000 now. So now I've covered my minimum and my maximum. That's why I had to highlight those, is because if I'm going to tell Excel what ranges I want, I obviously have to, or I want to have the beginning be below the minimum and the end to be above the maximum. Now, I always forget, but Excel is going to dump some of these. I always forget if this is going to be the minimum range or the maximum of the range. I think it's going to be the minimum. So we might not actually get any data above 18,000, but we'll see that in a second. But now, if I go to data, data analysis, we get this menu of cool stuff that data analysis does. What we want to do right now is make a histogram. So I'm going to click on histogram right here. Click OK. My input range is the data that I want to make the histogram for. So that's going to be this deaths per 1 million population. So I click, or sorry, I'm doing tests. No, sorry, what am I doing? I'm doing cases per million population. Let's make sure that's actually what I highlighted. Did I highlight that? Yes, I did total cases. So that's what we're going to make our histogram of. So data analysis, histogram. So I want total cases per million population. I click on the label or the title. And then what I did, a quick way to highlight a column from top to bottom is you click on the label and then you do Control Shift, or sorry, Shift Command down if you're on a Mac, Shift Control down if you're on a Windows machine. And now I have I1 to I101. So I1 to I101. That also tells us how many countries we have, right? That's how many countries are in this data set. 100 countries, because I included the label. Because I included the label or the title of the column, I have to make sure to click this right here. Otherwise, Excel is going to complain and be like, hey, you gave me a value that wasn't a number, and I'm trying to deal with numbers here. So output range, or new worksheet, this is just where do you want it to put the histogram that we make. And bin range right here, this is why we had to make these bins. This tells Excel how to categorize those different total deaths per 1 million. That gives it the ranges, and that'll probably make a little bit more sense once we actually look at the histogram. So now we cross our fingers before we hit OK, because we always can make mistakes when we're doing these things at Excel. It's trying. So it looks like it worked. I don't understand why we're not getting that value up above for our maximum, though. So let's find that maximum. So there it is. That's 17,000. Oh, it's because I got stopped right here. I was wrong about the countries, so we actually need to delete this row. That's the Diamond Princess. So actually this data set includes, that's a cruise ship. that had the coronavirus on it. So that's one problem that can occur if you have missing data. So these are all good ways actually. We need to figure out if we have missing data. So it looks like that was the only missing one. And now we need to redo our histogram because we didn't go far enough down because of that missing data. Because watch what happens now. If I go click on total cases, Control Shift down, now it's going to 203. So I actually have 202 countries, which is basically every country in the world now. And now let's try pushing OK again. And there we go. There's our one huge country. Notice that that is a major outlier in our data set relative to these other countries. So this is going to be a really skewed distribution, actually. And notice this doesn't actually make the histogram. Oops, looked like I froze. I always freeze up on you guys about halfway through, so I'll disappear myself. So let's go ahead and now make the way we actually show the histogram is we can highlight just the frequencies for now, insert, and do a bar chart. And there's our histogram. Make it nice and big. And we can see this data is super skewed, we say. So you usually want to make a chart title. This is a histogram of confirmed coronavirus cases by country. So what this tells us is the vast majority of countries just have a few. Actually, let's insert another thing we can do is if we select data, instead of having, notice it just went 1 to 36 because there's 36 different categories, but it'd be a lot easier to put these bins on here. And then if we push OK, this is going to be a more informative graph now. Let's make those bigger because now it actually tells us what that x-axis represents. So I can make those a lot bigger so we can see them. So notice the vast majority of these countries have 500 or fewer. So actually this is going to be 500 to 1,000, I believe. Or actually we can figure it out. So we know that that one case is less than 17,500. So that's recorded in the, I'm going to delete this sheet because this was our bad histogram. So notice that's recorded in the 17,500. So this 500 actually represents between 0 and 500. So this bar says that actually a majority of countries have between 0 and 500 confirmed coronavirus cases in their population. And then we kind of tail off. There's quite a few countries still. So 17 countries. If I hover over this, it tells me the value. Notice this one, 133 out of our 202 countries have between 0 and 500 coronavirus cases per million people. 17 have between 500 and 1,000. 13 have between 1,000 and 1,500, and so on. Only one country has between 17,000 and 17,500. One country is out here. Try to hover over that, and that's between 13,500 and 14,000. One country out here. So these are pretty big outliers, right? Now what I want you to notice is this is absolutely not a bell-shaped curve, right? So this is not a histogram of sample means. This is the histogram of the underlying values. Kind of like when we rolled the dice and we looked at one value at a time. We got that rectangle, that uniform distribution. But then when we took averages, that turns into a bell curve. So in the real world, when we're looking at data and we want to get our point estimate of the population mean, which we call the sample mean, we're not actually going to be able to produce a histogram of this estimate because we're only going to take one average. I'm going to take the average of this column, total cases per million. And the average is 944. So notice that these outliers, although most countries have less than 500 cases, the average is much higher than that. And that's because these outliers pull that average way upwards. That always happens when you have a skewed distribution. Sometimes when you have a skewed distribution, it makes sense to look at the sample median, by the way, equals median. And that's 188. When we have a skewed distribution like this, the median is always much less than the mean. Because the median is unaffected by outliers, the mean is affected by outliers. But this number right here, although we only get to see one observation from it, we know from theory that this number comes from a normal distribution. Okay? So now let's get sigma. Sigma is our population standard deviation, and we can even, if we do insert and find a symbol, we can probably find a sigma in here. Come on, Greek letters. Oh, I don't have sigma up there anymore. Why would somebody want these emojis instead of a cool Greek letter? That's just weird. Come on, cool Greek letters. Flags before Greek letters? What is happening to the world, people, where Greek letters are after dominoes? Come on. I can't even find Greek letters. Oh, those are kind of like some Greek letters. Come on, sigma. How long do you guys want me to spend looking for this? Let's just go ahead and call it sigma and not worry about the symbol. I promise you can actually find this symbol for sigma. But that's going to be, let's actually write out what this is. This is the population standard deviation. In the future, we're going to use what's called S, which I mentioned in the other part of this video. But standard deviation, P for population standard deviation. I'm going to go ahead and highlight that same data. This is the standard deviation of the underlying individual values. So let's even be more clear about this. Of individual values. That is not the standard deviation of sample mean, which remember we call that the standard error. That's not that yet, because what do we have to do from that formula that I showed? We have to do equals this divided by the sample size, which we can count the number of observations in this column right here. And that gives us the sample size. That's how many observations we used to calculate our sample mean, n, our sample size. So there is our standard error or our standard deviation. Notice that's way smaller than the underlying one because we took a big sample. Our sample was more than 200 countries. So this, although it's good to know those formulas, those underlying formulas, in the real world when we're doing statistics, we like to do stuff with computers and Excel. We do not like to sit and scratch out really long formulas on scratch paper. We go to Excel and we crank out numbers. And so this is a real world phenomena that's really important right now. I got this data today. We calculated a point estimate of the population mean. We calculated a median just for fun because it's important to do that oftentimes when you have a skewed distribution. We recognize from theory and from intuition that we looked at in the notes, that this number, this 944 cases per million population, comes from a bell-shaped distribution. We only have one observation of that number, so we can't go actually look at that histogram, but we want to remember that every time we calculate a sample mean as a point estimate for a population mean, that sample mean comes from a bell-shaped curve. That bell-shaped curve is centered at the population mean, but we don't exactly know what the population mean is because, note, we're going to have more cases in the future. So it's not really clear what the true population mean is going to be yet, but this is our estimate of it. We also like to know how spread out that bell-shaped distribution is, and we measured that using our standard error. The standard error is this 9.87 right here. So these are the ways we actually calculate those numbers in the real world. So today we saw the notes and learned where these numbers come from, but then we cranked them out using Excel, which is what we really want to get used to in this class. All right, I'll see you guys soon.